Thanks a lot for the intro, Alex, and welcome everyone to this webinar. Hope you can hear me clearly, and if any issues, of course, that Alex mentioned, you can paste it in the chat or ask the question. So I think, yeah, I'll just get started with this webinar and talk about Singularity. I won't make any assumptions on how much experience people have had with HPC or virtual machines or cloud or Singularity, things like that. So if I use any sort of acronyms or something, definitely feel free to ask what something like that means. But yeah, it's an interesting webinar for me to present because Singularity is something, I guess now it's well matured to an extent where it's fairly usable and pretty widespread in the HPC community for containerization of HPC workloads. So it's expanded quite a bit. Probably what you've heard about more than Singularity is Docker. So definitely while developing this webinar, the initial thought was, hey, Docker is the most popular containerization solution. Let's look at that first. But then started leaning more towards Singularity, primarily because the use cases in our community, which is all of you, leans more towards high performance computing, scientific computing, running computationally intensive workloads, whether they're CPU or GPU, memory, et cetera, et cetera. So Singularity made more sense than Docker, although you could still use Docker. And if you're using that, definitely would love to hear your reasons. But I think Singularity is a great solution for certain problems that you're trying to solve. I definitely would emphasize it doesn't solve every problem, but in certain cases, it's extremely useful and definitely can help you out in whatever type of research that you're doing. So I think in terms of just an outline, I'll talk a little bit about containerization, a little bit about maybe the history of it, and then I'll show you a demo, which I kind of selected because I thought, hey, I should show you a demo that actually reflects some real world use cases versus just what you can find in the tutorials and things like that. And last thing I'll mention is last year as well, my colleague at WestGrid from the University of Manitoba, Gregory Shamoff, also presented on Singularity. And prior to that, another colleague at SharkNet, Paul Prini, presented on Singularity as well. So these webinars that they presented, I definitely, after this, encourage you to maybe look them up. I have a link to the WestGrid YouTube channel at the end of the slides. Have a look at those as well. They're more of an introduction to the very basic concepts of Singularity, how to build containers, how to run containers, et cetera, et cetera. But they use example workloads that are mostly from the user documentation. And I was trying to avoid that for this webinar and try to present something different in terms of at least showing you, hey, this is a real world use case. So those definitely are useful as introductions, and this is maybe more a supplement to those webinars that were done last year. So definitely look those up. So with that being said, I'll get started and go to the next slide. All right, so the title of this webinar obviously talks about virtual machines, right, and HPC. So we'll tie those together in at the very end of this, but I think I'll first talk about virtualization, which is your standard kind of some paradigm. Maybe early 2000s, it started getting popular. Around 2010, everyone was doing it. And we've seen shifts towards containerization, maybe at the beginning of 2010s up till now, and a movement towards that. But the simplest form of it is you have hardware, your CPU, memory, disk, networking, etc. I call those infrastructure. And then you have something that sits on top of them called a VMM or a hypervisor. And you can run your operating systems on top of that. So this is heavyweight virtualization. So you have piece of hardware infrastructure, you run operating systems on top of it. And if you've ever used Compute Canada Cloud, that's exactly what it is. It's a virtualization platform that we're running OSs on top of. The OS could be Windows, it could be Linux, could be BSD, whatever you think it is. This is one way of running your workloads. You can have a full heavyweight OS, install Linux on it, run your scripts, run your software in there, and go from there. That's one way of doing things. And it's a perfectly legitimate way of doing things if that suits your workflow and your understanding of how all this works. So there's nothing wrong with doing that. It's fine. In some cases, it's actually simpler than containerization, but there is some cost to doing it like this. All right. Now, containers is a little bit different. than heavyweight virtualization that I showed you earlier. So containerization is OS level virtualization. What that means is you have an additional layer of abstraction. So you have an OS, which in this case with Singularity, we're going to be dealing with Linux because that's the OS that's kind of ubiquitous in the HPC world. But you have a container engine that sits on top of the OS, and OS sits on infrastructure. Mind you, that infrastructure that I have at the bottom there, it could be bare metal. So it could be a server sitting in a data center somewhere. It could be a cloud VM, or it could be a private cloud VM sitting in your data center. So the infrastructure could be virtual or real, but you have an operating system running, then you have a container engine running on top of that operating system, and you have your applications and libraries running on top of that container engine. So one of the beauties of this approach is because you have your applications and libraries containerized, they have to be compatible with the container engine. And whatever platforms that you have an OS, as long as they support that container engine, you can run your applications. I mean, in a sense, it sounds too good to be true almost, that you have true write once or run anywhere. I think back in the day, Java virtual machine was kind of a first attempt at this and didn't work that well because there were incompatibilities. And yeah, in this case too, sometimes you come across things that don't work seamlessly. And I can definitely describe some of those things. But for the most part, you can focus on building out your applications and libraries that actually get the work done, the research that you're doing, and containerize them, package them up into a container, and run that in the container engine. So you don't have to worry about the underlying operating system or the infrastructure, and you can go from there. As I said, it doesn't always work perfectly, but in a lot of cases, it works pretty well. All right. So containers themselves, they don't require virtual machines. I mentioned earlier, they can also run on bare metal. And if you actually try to run something like Singularity on the HPC systems that we have, whether it's Cedar or Graham Beluga, you actually are running on the bare metal. But you can also run them on Cloud OS, like Arbutus on OpenStack. And that's because the containers only expect an operating system to be present. They don't care about the hardware that's underneath there, right? So the main advantage, I would say, of containerization versus the full heavyweight VM solution for running workloads is it's very lightweight because you share the same operating system kernel and you have an interface to that kernel. So you can run a lot of containers with different workloads on a single OS. So your resource utilization potentially is better. Not always, but in a lot of cases it is. But the primary reason why I think it's useful, and the reason why when I was developing this webinar, I was actually thinking, what's the purpose of this research? This is very cool technology. It's awesome. You can do a really good show of it and all that stuff. But how does it actually help with the research use cases? So portability was something I really latched onto, is that portability nowadays, I think, is pretty important. And the reason why I say that is I actually want to, so I see a question from Ben. And actually, Ben, I'll answer your question about CUDA and GPU drivers. There's actually a slide on that, and I'll actually describe how it actually works with that. But it's a good question. I'll get back to you in the next few slides on that. But portability is pretty important because right now, and I can tell you this is a real world use case, and I've dealt with this with a lot of researchers at UBC especially. I'm sure it's the same at whatever institution you're at, in that Compute Canada is a great organization. It provides a lot of resources to researchers, but everyone wants more. Everyone wants more resources. So a lot of times researchers will say, okay, you know what? I have my own on-prem cluster, or I have my own on-prem cloud, or I potentially have a public cloud like Amazon. Amazon or Microsoft say they want to do a partnership with me and provide me with these cloud credits to run. So you have your workloads running perfectly on Compute Canada systems, but it's not enough resources for you. You want to run on cloud, you want to run on virtual machines, you want to run on your own cluster, so forth. One way of approaching this problem is, okay, I'm going to build all my software separately on each of these systems, configure it and tailor it to run on each of these systems, and there, I'll do that. And that's a perfectly legitimate way of doing it. If that works for you, definitely, it's not a wrong way of doing things. But containers are kind of nice because you can build a consistent stack of software, or you can use something that somebody else has built which is even nicer. And you can actually run these across your multiple platforms, whether it's HPC, Compute Canada, whether it's some other HPC system, whether it's the public cloud, whether it's the private cloud, and so forth. And you're running the same versions of all your applications and your libraries and so forth. There's some caveats to that, and that question that Ben had in the chat about the GPU drivers, definitely that's one of the caveats. There's some other ones, but generally speaking, you're guaranteed some level of consistency when you're building this out, right? So your actual workloads, you're using the same versions of the software, and some workloads are sensitive to that. You might have potentially a different result if you use software with bugs and things like that. So portability was what I zeroed in as to why containerization is good. And it definitely has a lot of real world use cases, especially now, where I think we're undergoing a little bit of a paradigm shift in computing. And this doesn't apply just to advanced research computing or HPC in general. Is you'd think the early 90s, it's all hardware. 2000s, we started looking more at virtual machines and virtualization. Then maybe mid 2010s started looking more at containerization. But now a lot of stuff is moving towards cloud, whether it's private or a public cloud. And cloud is becoming the place to actually run your applications. And even from a scientific perspective, HPC, I wouldn't say that bare metal HPC would ever go away, but there's a lot of supplementary options to run that and those type of workloads in the cloud. So we're definitely seeing the shift towards that. I expect from what I've seen, that shift to accelerate as we go forward. So how do you get these workloads to live and to run and exist and work well in this, this new world, this new paradigm that's being created? All right, so portability is huge. So the other reason, or maybe a couple of examples I can give you, and these are also real world use cases. One is, a researcher has very specific requirements for their workloads, very customized software. I think we try to provide as much, general software, CVMFS, if you've used the Compute Canada system, it's a great way of providing a very consistent set of software for researchers to run. But let's say something very esoteric comes along. How do you run this, right? Yes, you can build it on the system, but they want to run it in different places. Containers is a great option. Another example would be you have a very old piece of commercial software. Maybe it requires, just as an example, Red Hat 5.2. I know probably nobody is using that anymore, but let's just say it's compiled and linked against those really old libraries, right? How do you actually get that to work? Containers, another option for doing that. You could do a heavyweight VM as well, but containers work pretty well too for that. I think the bottom line I would say is, generally speaking, is, which I emphasized at the beginning, is while the technology is very cool, use it when it makes sense for your workloads, right? It has to make sense for what you're trying to do. I think in a lot of cases it can make sense. In some cases, maybe it doesn't make a whole lot of sense to do it, right? And hopefully the examples that we provide in this webinar will actually say, hey, that actually looks something that can inspire me to say, well, these containers actually make sense. Maybe I can apply this in a real world use case. So I deliberately left out the examples from the user documentation, because I'm sure all of you can go there and run the echo hello world and so forth. I think that's not what you're looking for here, but you can definitely do that as well if you want to get a taste of it. But I'm trying to do some more real world solutions here. All right. So the big 4 reasons why containers are good, I'll use that word, it's a very ambiguous word, but I'll just say they're good, is first of all, reproducibility. Now, when you're doing research, a lot of times you're linking various versions of libraries, operating systems, Python packages, commercial software, R packages. You might have this quite complex workflow with very specific versions of software. It's good for reproducibility, because when you publish those results, how did you arrive at that particular set of results? What pipeline did you actually use? You could have a container with its definition files, check that into your Git or your version control system and say, hey, this is exactly what we use and this is how we produce this result. And let's say you find a bug in your work, you have to go back and see why you're encountering that bug. You'll be able to see that from a previous tag of the container version and so forth. Secondly, which I mentioned and actually talked about already at length, was portability. run it across different platforms, regardless of what they are, whether they're virtual machines in the cloud or whether they're HPC bare metal systems. Portability is key. Third, isolation. Now, this also applies to virtual machines, and virtual machines actually have more potentially isolation than containers because they don't share the kernel. But isolation is key as well, is that you can run multiple containers on the same host and you can keep them isolated from each other. So there's some security there. Of course, you guys have probably heard, because it's always a breaking news story, when there's some privilege escalation attack on Docker as to how somebody escaped from a container and got root on a system and so forth. So it's not foolproof, but there are various mitigations. I won't speak too much on security because that definitely I would say I'm not a super expert on that, but also because it's quite a big topic with containers. And Singularity in particular, it actually takes some pretty good default sensible measures to make sure it runs securely on your system. Obviously, there's always ways where that can be circumvented, but I find Singularity has a pretty good design philosophy that kind of reduces the impacts of those. And fourthly, and this was one of the reasons why we're actually doing this webinar, is just to show you how you can avoid complexity. So containerization can introduce complexity, but it can also avoid it. I don't know how many times, if you guys have tried to install an application, and Python is notorious for this, but the other software as well. It has 50 dependencies, different versions. It needs this library version that works on this. You might try installing it on the Compute Canada systems, and there's a Python package format called Many Linux 2010. It doesn't work with our system, so you've got to convert that package into a different format to use it. So Python wheels, for example. So a lot of times you go down this rabbit hole of like trying to satisfy all these dependencies with complex software. And one of the demos that Alex will be showing later, the Topology toolkit, it's a very hard piece of software to install for anyone who's using it. So it's a huge number of dependencies. Other types of software, a lot of these deep learning frameworks and stuff, not straightforward to install. So sometimes taking containers that other people have developed, modifying them, or maybe just using them straight, you can avoid that. And a lot of times the developers of this software, like for example, PyTorch or TensorFlow, they provide official releases of these containers. NVIDIA is pretty good for doing this because NVIDIA has its own container registry as well for all the software that they support on their GPUs. And what's great about NVIDIA is NVIDIA actually, they really strive to make these things as portable as possible. So whatever platform you're running on, as long as it has a compatible GPU, it generally will run. So complexity is there when you introduce containers, but you can also save you with a lot of complexity, especially if you're using pre-built recipes and pre-built options for running your containers. All right. So Docker, this is kind of the big elephant of containerization technology. It's the most popular solution. Got a large number of users, and it's really what opened the door to containerization, because Docker made it accessible for people that don't have a lot of experience to use containers. That was good and bad in a way, in that there were some bad solutions that were created with that in the early days, but right now it's pretty mature platform. Uses standard Linux functionality available in later kernels, like C groups for memory management, kernel namespaces, and a union file system. So let's standard features available in most of the later Linuxes available. It leverages those to work, and it's extremely mature. So Docker Hub is kind of the registry where you find all user contributed containers maintained by the vendors, et cetera. There are about 7 million active users on that platform, probably more. That number is out of date right now. So when the user count gets into the millions, this technology is well tested, it's very mature, and so forth. All right. And this is just a little diagram of how Docker interfaces with the host OS, the Linux kernel, and some of the features that I mentioned earlier, like C groups and namespaces, and how it uses the network. So there are various libraries like LXC and libvirt you can use to interface with the underlying operating system. But in a nutshell, Docker is fairly plug and play at this point. You install the Docker engine, you can download some containers from Docker Hub and get them running. So there's a lot of good stuff there. So I definitely recommend, even though this webinar doesn't focus on Docker, definitely check out Docker as a potential option, especially for persistent services. You're running a web server, you're running a database, potentially Docker is a better option for running services that are persistent and long-lived, that serve data and so forth. Now, Singularity, which is what this webinar is about, this definitely was developed as an answer to the containerization issue in the advanced research computing space, right? A lot of the work that we do in ARC, it's batch driven. You have some data, you have some algorithms, you have some software, you have to run it, process it, and your job starts, your job ends. That doesn't tend to be the way Docker works. Other thing about Docker is it needs a Docker daemon. So what a daemon is in Unix computing parlance, it's actually a process that runs all the time with potentially an elevated privilege set. So you need this to run on every node that hosts a Docker container. So a node could be a bare metal Linux server, or it could be a cloud VM. So this daemon, it's not a good fit for HPC solutions, because security is one issue. Second thing is you have it running there, configuring it to mitigate some of these security concerns, actually limit some of the feature set of Docker. So the design philosophy is different, or the usage philosophy is different from what we generally see in high performance computing. And there's a document on Docker Hub, if you're interested in the security part of this, which I definitely recommend reading. So how you mitigate some of these security concerns. The second and probably the biggest reason why Docker, or Singularity was created as a response to this was Docker doesn't provide close integration with, our standard software stack. So two big software stacks in the ARC space or the HPC space are MPI, message passing interface, and the schedulers and the resource managers, Slurm and PBS Pro. These are two of the most popular ones. So we use Slurm in the Compute Canada systems. At UBC on our Sakai system, we use PBS Pro. A lot of software is written to use MPI in mind. These types of software stacks, they cannot be replaced overnight. Like, these things have been built over decades of time, and there's huge amounts of investments, both from commercial software, open source software, researchers, et cetera. So you needed a solution that could actually support these out of the box. Singularity gets close. It's not perfect, but it does support these and has pretty good integration with both the scheduling systems and resource managers, as well as MPI. Now, you guys have probably heard of something like Kubernetes or Docker Swarm, which provides some scheduling functionality for Docker containers and so forth. So you can use things like that. I'm not saying Kubernetes or Swarm is a bad idea, but they generally don't fit the philosophies of something like Slurm or PBS Pro, which are really batch driven. Those are more, again, I would still say persistent type of services, right? So they don't match the feature set. And once again, the investment in decades over things like MPI and Slurm, you can't just get rid of that when you move into the HPC space. So Singularity was designed with those in mind, whereas Docker wasn't. All right. The Singularity is pretty nice. It was developed at Lawrence Berkeley National Lab, but it's been spun off into a company right now, which is, I think it's called Scilabs. So there's actually a company that's doing all the development work on it. One of the big design decisions was there's no daemon process required. It's just an executable. So you can compile an executable. It is a set UID executable. You can compile it without set UID. That opens up another can of worms, and there's another security topic to discuss there, but I'll just talk about it a little bit. The user permissions model is what makes Singularity really good, because as the user, let's say you log onto a Compute Canada system, you have your username with certain types of privileges and permissions on that system. Singularity actually carries across the permissions that you have on the system into the container. So that definitely mitigates any sort of privilege escalation. HPC administrators are always worried about this because an HPC resource is a shared resource. If you have people that potentially could escalate their privileges in that system because it's a shared system, it's not a good thing. Bad things can happen. So user permissions model is a great design decision by the Singularity designers, that it definitely, you keep the same permissions that you have, which are your standard user permissions, whether you're outside the container or inside the container. Now, the two big features as well, support for NVIDIA and AMD GPUs. So you can pass the --nv or the ROCm flags the Singularity command line. And if there is a GPU, you definitely can take advantage of that as well. But there's a caveat there. The host and the container must have compatible versions of the drivers and libraries installed. So if you're using the version 10 of the driver, your container should also have that version of the driver and so forth, right? So probably point differences in the versions and the libraries doesn't matter too much. I haven't done too much testing on that, but if you're having major release differences in drivers and versions, it might work, it might not work. So generally, you want to keep those aligned. If you're using, CUDA 11.2 or 10.2, you probably don't want to have a huge separation between what's available on the host and what's available in the container. It might work, it might not. So generally speaking, I recommend keep those versions of the GPU drivers and CUDA libraries kind of matched up. I see something in the chat. So I'll get back to the chat question. It's a large question, so I'll definitely get back to that towards the end of that. So the other thing that Singularity actually supports is MPI. So the second thing is you can run on a single node, no problem. That's the easy part. Whether it's a GPU node or a CPU node, no issue. But MPI is pretty important as well, because a lot of software, this is its standard framework for running on distributed fashion. So there are two models that Singularity supports for MPI. There's the hybrid model. Both the host and the container must have compatible versions of the library. So this is super important for MPI, that if you're going to use OpenMPI version 4, you should have OpenMPI version 4 installed in the container as well. Version 3 might work. Sometimes certain features might work. They don't work if there's a different version mismatch. So best to keep the libraries same across the host and the container. The cool thing about the hybrid model is when you're running an MPI applications, you can do MPI run or srun, and you just pass the Singularity executable. Typically, you'd pass whatever executable you had if you weren't using Singularity, but you pass Singularity as an executable, it'll pick up that it's running an MPI and it'll just work. That's kind of the nice thing about it. The second way to do it, if you don't want to install MPI in your container itself, there's something called the bind model. And that's essentially you're mounting the MPI implementation on the host in the container. I haven't had too much experience with the bind model. I typically use the hybrid model, and the example I'll show you will use the hybrid model. But the bind model could also work in certain circumstances if the sysadmins allow it, right? If you're allowed to mount the MPI implementation of the host in the container, there's some security concerns. I definitely recommend reading up the user guide for MPI. It's quite comprehensive, but I find that the hybrid model works in most cases. So right now, just look at the question again that Vaibhav had asked. So can we control how many memories and cores can be used by the container? And I submit a Slurm job in HPC with 100 gigabytes and 16 cores. So you can control the memories and cores that are available to the container. That's the Slurm integration. So you have to specify in Slurm, like standard, like whether you're running a typical program, how much memory you want, how many cores you want, et cetera, et cetera. So you have to do that because you're still running within Slurm. So Slurm, the scheduler still controls how many resources that Singularity is going to get access to, right? So you have to request the resources, and you have, because Singularity is just another process to the scheduler. So to the scheduler, it's a process, just like you're running PyTorch outside of Singularity, you're going to run within Singularity, you still have to request how much memory, how many cores, et cetera, with Slurm. So you still have to provide a submission script that actually specifies all those options. So that's what you have to do. The actual application you're using, so yes, in a sense, it will get the resources that you've requested via Slurm. So does Singularity see the environment variables? It does. So Singularity does see the environment variables. As long as your Slurm integration is working, it should see whatever you have in your environment. The environment is actually carried on. I haven't actually tested these particular environment variables, but it should see those. Additionally, you can bind variables. You can set those up as well in the submission script, and it will see those. So Singularity will And if I'm wrong, it's probably a configuration issue, but it will see those. All right. Performance is something that a lot of people have concerns about when it comes to containerization. So I can definitely allay some of these. If you're running on HPC systems, there's almost no performance gap between a Singularity container versus directly running on the host system. So if it's bare metal, literally the performance difference is 1 to 2%. The Singularity might be slightly slower because of that containerization overhead. If you really want to see the details, there's been extensive benchmarking done on these, and I have links to a couple of papers that people have benchmarked. Mind you, when you're running on virtual machines like in the cloud, this might not be the case because virtualization introduces another layer. There hasn't been a lot of benchmarking work done when you're running on cloud systems or virtual machines, but I anticipate there could be a reasonable performance drop there, but there are other advantages to running on virtual machines versus just running on bare metal. But on bare metal, essentially, there's no difference in performance. So performance is still great. Now, what's the typical workflow when you're using Singularity? So Singularity, first off, you can use it for development. So you can build your own sandboxes, do your customizations in there. You can build from recipes. So people have published recipes on Git and so forth, and you can build recipes there. You can also build from Singularity Hub. So Singularity Hub is kind of like Docker Hub, which is like a registry of containers where you can pull containers down from there and build your containers locally. But then the real, I think, the killer feature of Singularity is you can build from Docker Hub. I find the container registry on Docker Hub to be the most comprehensive, and most of the developers are using that one. So you can pull Docker images and it will actually convert them into a SIF, which is Singularity image format, and it will run there. Now, finally, once you have your images, you can actually run them. So Singularity has a command called Singularity run. So you get an interactive session within a container, and I'll show you that a little bit in the demo. You can have a Singularity exec. So typically when you run with Slurm, you set up your Slurm submission script, and then you run Singularity exec to execute the container and all the commands that you want for the container. If it's MPI, you can use MPI run to prepend that, or srun, and that should work as well, as long as the scheduler and MPI are configured correctly. And the other thing you can do with this, you can push and pull changes to your Git repository, or you can commit changes to the containers and so forth and tag them with versions and then build new ones. So it's kind of nice because you can integrate this into your CI workflow. If you have like an integration workflow, you can do this and publish changes nightly to your work and so forth. So if you're a developer and you like using that type of agile methodology, I think Singularity is a pretty good solution just from a developer perspective, less so maybe from just a HPC perspective. All right. I should mention Docker Hub if you haven't heard of it. I talked about it a few times, but I think Docker Hub is pretty amazing because any software that you're really looking at, whether it's HPC software or just other types of software like Apache, et cetera, it's typically available here as a Docker container. And you can look at it, you can see the changes, you can look into it, you're looking at the tags and so forth. You can pull these containers down into Singularity and build them. Just need a Linux box with sudo access, and you can pull them down, build the containers, and just run them. So a lot of these things work right out of the box, that you don't have to do your own build work and make customizations and changes to the containers. They just work, and they work pretty well. Sometimes you actually have to change things around. Let's say it's a version mismatch for a driver that you don't have in your HPC system. You might have to go in there and modify a few things, but a lot of the times this just works, and it's pretty great that you can just grab these. And a lot of these are provided officially by the developers of the software, so you know there's some quality control around these as well. So Docker Hub, if you haven't checked it out, definitely use it. All right, just look at a few questions. We're about 35 minutes in, so we still have a bit of time. So let me just check out the questions. So somebody has answered the questions. Yeah, so Ben. Okay. So somebody had a question about porting from Singularity to Docker. That's a good question because I've often only heard of it going the other way, where people use Docker containers. I don't see why you can't do that. That should be possible just using the Docker build tools. You probably have to modify the recipes and make some changes to the way Singularity does things, but you can do that the other way. I've mostly done it one way because Singularity makes it so easy to take a Docker container and convert it. I honestly have not tried taking a Singularity container and converting it to Docker. So going the other way is something I'll definitely admit I have not done that. So I think try it. I don't think there should be an issue, but I do think there's probably some work required to actually do that. The other question that Ben had is, when I experimented with Singularity, it binds home user to the container, which has unfortunate side effects. Yeah, because you're storing your database on Cedar. So I think this is generally probably a Cedar specific issue because the home file system does get hammered quite a bit, right? It's a lot of people are using that file system. You can do other types of binds. You can do, but that has to be enabled by the system administrator. So on Cedar, I'm not sure if they're actually allowing you to specify your own binds or whether the binds actually, Singularity lets the sysadmins decide whether they want to allow users to bind outside of the paths that are allowed. If you're running on a VM, of course, you have full access. You can bind whatever you like. So I think the solution is to just try. You can specify a new bind point, maybe try it on Scratch. But I don't know whether Julia, you're able to set an environment variable that Julia can use another file system instead of using your home. So it's something to try about, but I don't know whether bind, because I haven't tried using custom binds on Cedar. I just use the default binds that are actually provided. All right. So virtual machines and HPC. This is kind of my favorite topic now because I attended Supercomputing 20 last year, and this is one of the biggest things that's going on right now is HPC typically is always run on bare metal to get your maximized performance, and that's never going to change. It's always going to stay the same because you always have applications that need to get that last bit of performance out of a system and out of the hardware. So you always have scope for that. But one thing I really noticed in the supercomputing space is that virtual machines, virtualization is becoming huge in the HPC world in that we've already seen it in our Compute Canada Federation. If you've ever used Magic Castle software, just developed by one of our developers, Felix Antoine at Calcul Quebec, it lets you run or simulate an HPC system on top of a cloud platform. So essentially on top of a virtual machine, you run HPC or high performance computing. This is pretty good because it's customizable, right? I need to spin up a cluster with with 100 nodes. If I have access to a large amount of cloud resources, I can do that and just spin up the HPC on top of that. You are never going to get as good performance by doing this because you're going through an additional layer of virtualization, right? But there are other advantages to actually doing this because you have infrastructure as code, which is a huge advantage. I can actually spin up an HPC system running on virtual machines and then run my Singularity container on top of that. So let's say I'm running on bare metal, I can port it to these virtual machines and HPC without too many changes, really. So the performance impacts can be mitigated. You can set some kernel parameters and so forth. One company that's done a lot of work, I definitely don't want to make it an advertisement for Amazon, but I definitely would mention that Amazon is a pretty popular option in this space for running your virtual machines and HPC because they have certain sort of performance mitigations that have been done to allow you to run HPC on their EC2 compute service in AWS, something called the Elastic Network Adapter and the Fabric Adapter, which provides InfiniBand type speeds in the cloud networks. You're not just dependent on Ethernet. So there are a few things that they've done with it that lets you actually get pretty close to bare metal speeds on virtual machines at HPC. And then you can run Singularity on top of that. So I mentioned earlier, portability was a big use case and pretty much is the theme. If you haven't noticed, the theme of this presentation is I'm saying portability, portability, portability. And the reason why I say that is because this is what, if you're in the support space like I am, researchers want to be able to run their workloads anywhere, and this is going to keep increasing. I have 4 different HPC systems in Compute Canada itself. I have Arbutus, I have Cedar Cloud, Graham Cloud, I have AWS, I have Azure, I have GCP, et cetera, et cetera. I might have OVF Cloud or some other cloud platform that my university provides. At BCNet, we have EduCloud. So you have so many platforms. How do you leverage all these platforms without going crazy, configuring and compiling and running on all these? Singularity, this is the way you want to go if you're in this space, is use Singularity, build your images, or use a pre-existing image, run your software. So whether you're running on virtual machines or bare metal, if you're using the HPC paradigm, this is always going to work. And yes, it's not perfect. It took me a while to actually get the demo that I'm going to show you actually running on AWS. I used AWS as an example because I wanted to go completely outside of the box with this demo. Maybe it's not so outside of the box for some of you, but for me, I wanted to run a workload on AWS just to see how it would work. All right. So what I decided with this demo was I found a tool called Horovod. So Horovod was developed by Uber. I'm pretty sure all of you have heard Uber, the car ride-sharing company. But they use a lot of deep learning and machine learning technology. They're pretty big in the space because you would think with all the self-driving cars and other things they're doing, they've actually contributed a fair amount of code with this. A lot of our users, whether they're faculty or whether they're students, deep learning, this is huge right now. And this is probably one of the biggest stressors on our resources at Compute Canada or at UBC, is that everyone wants GPUs, everybody wants to run, and they might be using a different framework like TensorFlow or PyTorch. These are two of the most common ones. If you're running on a single node, it's not an issue, right? But how do you scale this to multiple nodes? And how do you do training on multiple nodes? Because yeah, the more GPUs you have, the faster you can go. So the goal, take the single GPU training, run it in parallel. Horovod is awesome because it actually adds some libraries and some hooks for actually making this pretty easy. And it supports MPI as well. It supports another distributed framework called Glue, but it's good because regardless of what the underlying deep learning training framework you're using, you can actually run it on multiple GPUs using Horovod in parallel, all right? And the cool thing is there's actually an image, because if you go to the GitHub page for Horovod and you say, okay, how do I use it now? I want to build it. Look at the instructions. You're going to look at it and say, yep, I don't want to use this. This is too complex to build. It's too difficult. Look at all these dependencies and so forth. But the nice thing is the developers have put a Docker image in the Docker hub. So I want to bring that down to my system. So I've decided I'm going to run this on AWS, for example. How do I bring this down? There's a single command, Singularity pull, Horovod.sif, you can call that whatever you want, create a Singularity image file and give it the Docker URI. And you can get the Docker URI from that Docker website I showed you earlier. Single command, this builds a Singularity image. That's it. It takes some time because it's a fairly large image. So it builds that image out and you have it. That's all there is to it. And it sounds like magic, but it actually works. If I want to run it on a single GPU, execute this command, Singularity exec, you can see I'm passing the --NV flag to use the NVIDIA GPU on my system. And I'm just running a simple example with ImageNet ResNet 50 algorithm to do some training with a tiny data set of about 3,500 images. So single GPU works perfectly. As I mentioned earlier, just make sure your libraries and CUDA versions in and outside of the containers actually match. Might work if they don't match, but you might get some bad errors as well. So one line of code to bring something down. Now, this might not work with all the packages available on Docker Hub. Some packages might be badly designed, missing dependencies and so forth. But a lot of times you can pull in packages, at least to use as a base. If you don't like pre-built stuff, you can also pull in an operating system like Ubuntu or CentOS and use that and add your own stuff. But a lot of times I find, hey, just use the stuff that's built out there and avoid the dependency hell that's going on. All right. So I'm coming towards this because I want to leave some time for Alex to do his topology toolkit demo. But the distributed training example I'm going to be running, this actually is an example running on a virtual HPC. So a bunch of virtual machines that essentially are simulating an HPC cluster. So AWS has a tool called Parallel Cluster that actually spins up virtual machines on demand, hooks them up via the AWS proprietary network they have. It's called the Elastic Network Adapter. It's about 25 gigabits bandwidth over there. So not as much as InfiniBand, but good enough for this application. 8 GPU nodes. These are eight nodes with 1 GPU each, V100 GPUs, and they're called EC2 P3 instances, and using the Slurm scheduler and OpenMPI. So essentially a cluster as close as possible to what we have at Compute Canada, but running on virtual machines instead of running in the cloud, and Singularity on top of this. So this brings everything together. And the training example is a pretty good one because it's a real world use case and it's something that's quite in demand now. So here's an example of it actually running, and I'll switch my window to my web browser so I can actually show you some of the commands and so forth to get this to run. But let me just look at the questions now. So are there constraints on kernel versions, on system of different kernel compared to this? So definitely, yes, there are constraints. And the constraints mostly are caused by whether you install Singularity with set UID or not. Typically, if you do it with set UID, it's not too bad, you know, that you can run on older kernels. The problems really start occurring when you install Singularity without set UID because it depends on the user namespaces feature. And the user namespaces feature is iffy. It works well in later kernels, but in earlier kernels, user namespaces, there's some bugs, there's some issues. So things might not work the way you expect. So I find if you install Singularity with set UID, your sysadmin might not like that because they consider that a security problem. It works fairly well even with older kernels and different releases. But if you're going to do it without set UID, you have these user namespaces issue. And the user namespaces issue, later kernels, it works pretty well, but it doesn't always work out. So definitely that, in my real world experience, that's been the biggest problem with different kernel versions. All right. So I'm going to stop the share for a second just so I can show you the demo, because we're already at 48 minutes and I want to give Alex a little bit of time to do his. So I'll run through my demo fairly quickly and actually do a new share. All right, let's see where my... All right, so here's an example, and I hope you can all see my browser window. Here's an example of running that distributed training application I showed you earlier. Let me know if you have any problems seeing it. So I'm going to play this. So for example, this is my cluster running on AWS. I have 8 nodes running, and it's running with Slurm. Now, one thing I can do, as you see here, is I can actually execute Singularity run the name of my Singularity image file. So I have my Singularity image file there, and I get a Singularity prompt. So now I'm in my container. That's all there is to it. So I can go in my container and start inspecting things inside my container. So this container already comes pre-built with a whole bunch of examples. So one of the cool things is if I do an ls, it's mounted my home directory. So this is my home directory on the host, on the HPC VM that I already have it there. I can see all my files there. It mounts home by default. You can add other bind mounts, as mentioned earlier, if it's allowed. So I'm just going to show some examples here. So I go into this directory, I see the Git examples, and I'm just going to look at the PyTorch example. And this is within the container. This file system here only exists within the container. And you can see I'm going to run this example, ImageNet ResNet 50. And this is a distributed training. It has that all built in using Horovod. All right. So you can exit out of the container just by quitting out of it. Now you can see here are my submission scripts. So I have a submission script. It uses MPI run, and I have a training script that calls this Singularity exec, and you can see it's calling Singularity exec with the training directory and with the validation directory. You can see the --NV for the NVIDIA drivers, my CIF file, which is my Singularity image, and it's Python. So it runs Python within that container, right? So I have my MPI run, and I have my submission script, and then I can submit using sbatch and specify the number of nodes that I want to run. So here I'm actually submitting with sbatch. I want 8 nodes. I'm going to run my code. So I submit that, and you can see with SQ, it's actually running now. And I'm going to have a look at my Slurm output to see what's going on. So you can ignore these error lines here. The reason why I'm getting these lines is I'm using the software called ASCII Nema for recording, and it actually threw some of these errors. But you can see now my training is actually running. And then if you, I don't show this here, but if you SSH into each of the nodes that are running it, you'll see the NVIDIA SMI command. Each GPU is being pushed to about 70 to 80% of its limits. And you can see I'm training epochs. I set about 20 epochs to train, I think, in the training script, and it's running. So this uses data parallelism, where the image set, about 3,500 images, is just split up across the nodes. So you're using more GPUs, but you're going to get your training done faster. Because yes, there is some communication overhead, but because you have 8 GPUs instead of just one, you'll run through this quicker. And all of these nodes, the cool thing is they are virtual machines. They don't exist in reality. Yes, they're hooked up via pass-through to a V100 GPU. They're running in the public cloud. They have an HPC scheduler, and all of them use the same Singularity image. I've made no changes to the Singularity image. I downloaded it from Docker Hub, and that was it. And it actually just runs and it just works. I'm not going to say every example will be as easy as this one, because some examples you pull from Docker are definitely not going to work, but this was pretty awesome. And if you're in this space doing a TensorFlow or PyTorch, I definitely recommend checking out Horovod and Singularity, because this might be a really good use case. So I think I've overstepped my time. I want to give Alex some time, so I will stop sharing my screen now, and I'll hand back to Alex for his demo.
Now, can you see my slides?
Yeah,
TTK?
yeah. This time it's good.
Thank you. Yeah, thank you very much. All right, so I'm going to show you a live demo, and hopefully things work well, because it's actually quite a complex live demo. So the Topology toolkit is a software application that lets you analyze multi-dimensional scalar data set, do topological analysis. So it could be one-dimensional, two-dimensional, three-dimensional data set. And it's an open source project that was in development since 2014, so released 2 years ago, and it has a number of interfaces. You can use it from C++. You can use it from C++ with VTK, but probably the most popular approach is to use it from ParaView. So it's integrated into a special version of ParaView. And the way you install it natively, if you want to compile it yourself, first of all, you have to install a bunch of dependencies, quite a lot of dependencies. Then you'll need to download and patch ParaView source code. You cannot just use the off-the-shelf ParaView. Then after patching, you would compile ParaView, and then you would compile TTK. And it's not as straightforward as TTK documentation says. So it actually took me, when I was looking at this last November, it took me 3 full days to figure out which extra flags I had to use. And it's really difficult. So fortunately, there is a simpler solution. If you want to run ParaView and TTK on your own machine, the developers of TTK actually built a special Docker image with ParaView server and TTK. So the way you run it, you run TTK with ParaView inside ParaView server inside a Docker virtual machine on local port 1111, and connect to it from a local ParaView client running on the same machine. So, and that way you don't have to build anything. It's just you use off-the-shelf precompiled components. So now ParaView can also let you work with client in client server mode. So where you run the client on your computer and then the server on a, let's say, HPC cluster, if you want to process very large data sets that you cannot fit on your machine, or the amount of processing is just way too large. So in these cases, you run a ParaView server on the remote machine, and of course, you can run a specially patched version of ParaView server with TTK. One option would be to compile this on the cluster, but of course, compiling this on cluster will be a nightmare. So fortunately, a much simpler solution is to take the same Docker image that I mentioned before, and you can convert it into a Singularity image, and then run the ParaView server plus TTK inside the Singularity container on one of the ports on a compute node inside a Slurm job, and then connect to it from a client on your machine. So to run a ParaView, this is a special version of ParaView plus TTK Singularity image, you will need to pull a Docker image. And the way you would do this, you will go, as Venkat mentioned, you will go to Hub, the Docker Hub. And here, so once you log in, you simply search for Topology toolkit. Topology toolkit. Let's see if it finds something. And it will find the Topology toolkit. So you're going to use this one, for example. and I click on tags. And the thing that you're interested in is the version number. So there are different versions available. And in this demo, I'm going to show the latest version, so which is this one, ParaView 5.9.1 Docker image with TTK 0.9.9. So the latest ParaView and the latest TTK. And the way you build the Singularity image, well, first of all, actually, until this presentation, I didn't know about the Singularity pull command that Venkat mentioned. So this is nice that you can actually pull a Docker image from Docker Hub directly from Singularity. So I use a different approach. I use a standalone tool to pull a Docker image, which I guess was probably the only available option until Singularity built in right into the Singularity tool. So anyway, you download the image that you looked up. So the tag version, the version number is important, and then you create basically you pack everything into a tarball. And then you load the Singularity module, and then you run the Singularity build command. So this will build the CIF image, Singularity image. And ideally, you want to do this not on the login node, but on a compute node, because this is quite CPU intensive. So in this case, it actually turns out that to do this, it was sufficient for me to use 2 CPU cores, and the runtime was under 15 minutes. And it successfully built the CIF image, Singularity image. And then the important thing is when it's doing it, you want to wait for build complete message, so you know that you have the image built, and then you can delete the original tarball. So the demo I'm going to show you is already built the Singularity image, and in fact, it is right here. So this is the Singularity TTK ParaView plus TTK image, so ParaView 5.9.1. And it's just under 500 megabytes, as you can see, the Singularity image. So I already started a Slurm job. So it's a very small serial job on CEDA, interactive job with Salok. And inside this job, so I went into Scratch TTK, where I have all these files prepared. I also have the data set that I'm going to load. So this is a polygonal model of a dragon from one of the TTK tutorials. And what I'm going to do is so inside this job, I'm already running inside Slurm on a compute node. I'm going to load the Singularity module, and then I'm going to launch, I'm going to run Singularity run. So I'm going to run previous server, so the previous server from inside Singularity, and I will bind the classes home and Scratch directories. And I want to bind Scratch because my data set is on the Scratch file system. So what this will do, it will actually start the serial previous server. And we should probably give it around 10 seconds, 20 seconds, and it will display a message that the server has started and waiting for an incoming connection. And so I'm running right now on compute node 768, and I also want to organize in a separate terminal window. I'm going to organize SSH port forwarding from port 1111 on my computer to similar name port on the compute node on the cluster where I'm now running the private server. Waiting for incoming connections, so it says accepting connection. So I'm going to do that, organize SSH port forwarding. And now all I need to do just connect to the same port 1111 from ParaView client on my machine. So let's see, where's ParaView? I have it on a different window. Just give me a second. I need to drag ParaView. So here's my ParaView running, and I'm going to connect. So notice what's happening here. So I'm going to say connect to local host port 1111. I'm going to say connect, and it says client connected here. So right now, ParaView needs just a few seconds to set everything up to establish the client server connection. And then now, now it says that it has the following plugins available. So if you go down the list, you will see that there are a bunch of TTK, they're buried somewhere in the menu, plugins. The idea is that some of the plugins are available on the server side, some of them are available on the client side. I just close this window. I'll make ParaView full screen again. And then what I'm going to do here is so instead of loading the data set, I'm going to load the state file. So the state file is a local file on my machine, but it's set up in such a way that when I load the state file, it will load the remote data set on the CEDA Scratch file system in this directory, actually TTK subdirectory, and it will do the analysis, topological analysis of this data set. So I'll go to File, Load State, and when I do File Load State, it will actually browse the local file system. So state file is a local file, and it's this guy that I built yesterday. So it says use state data file option. So I'm just going to confirm use file names from the state. But if you want to choose file names, what you can do is you go to choose file names, and it says, so on CEDA, on Scratch file system, under Razumov TTK, dragon.etu is the file that I'm going to read. So anyway, I'm going to say OK, and it's just going to take maybe, I don't know, 10, 20 seconds to load the data set. So it's loading data set into the preview server on CEDA, and it's running the topological pipeline on this guy. So let's just give it some time. So the data set is few megabytes, but it actually is running quite a few filters. So it's doing a bunch of analysis. And here we go. So here I just loaded a topological. I load a, oops, it's quite slow when I run Zoom as well. So I loaded this polygonal mesh model, and then on top of this surface, on this surface, I initiated a scalar function, and then I run topological analysis on the scalar function. So it's the surface of this polygonal dragon. So I find the critical points, minimum, maxima, saddle points. I find the separatrices, and so separatrices are the special lines that separate domains of manifolds, ascending and descending manifolds, and then I color these manifolds in different colors. So all of this is done on the remote server, not on my machine, on CEDA, done by the special build of Purview 5.9.1 with TTK, all TTK filters enabled, and all that is running inside a Singularity container inside a Slurm job on a compute node. And as you can see, it's running pretty well. So even though I'm running this demo live along with Zoom, it's actually quite responsive. So yeah, so that's all I wanted to show. I think I will, unless there are questions about this specific demo, I will give the microphone back to Venkat.
Thanks a lot, Alex. That was a very cool demo, just to see that you're running Singularity in interactive node and actually doing visualization with it. I think there's nothing much that I have to add other than the slides will be posted, and you can definitely contact us if you have any questions on this, standard Compute Canada support channels or via WestGrid. And if you're really interested in using this technology, definitely get in touch with us, and maybe we can work together and see how it could work for you. And thank you so much for attending, and I will maybe give the closing words back to Alex.